Like all the Clickable Calculus webinars, this Multivariate Calculus webinar has two goals. First, clearly, you want to show some of the Maple tools relevant for multivariate calculus. And second, we want to show how resequencing of skills and concepts as, as applied to the multivariate calculus course can be implemented in Maple. Now, this phrase, resequencing of skills and concepts, comes from the literature. I first came across it in the late 1980s when I was getting started bringing Maple into the classroom. It means that instead of stressing the development of manipulative skills, which are needed to learn concepts in the traditional process, traditional course, we reverse the process. Put the initial stress on developing concepts, and you put the manipulative skills second. That way their purpose is seen in light of the conceptual understanding that came first. Now you can do this if a tool like Maple is used for the manipulations needed when you're juggling the concept and poking it around and looking at it from one side and another. And I found it best to implement the skills in Maple first, then you get a big picture approach where the brushstroke details are supplied by Maple. Then mastering the appropriate manipulative skills becomes easier because the implementation and the necessity has already been seen. Typically, a multivariate calculus course starts with a unit on lines and planes, vectors, lines and planes. So let's pick one of these problems from the section vector, lines, and planes. I've picked this one down here. Find the distance between two parallel planes. So you can see that the equations of the planes differ only by the constant at the end. They're clearly parallel. Let's begin with this interactive solution. So to make use of these tools in Maple, I want to load the student multivariate calculus package, tools, load package, student multivariate calculus. Maple has over 100 packages. It's just the library bundled into nice little clumps for bookkeeping purposes. It's all part of Maple. Okay, so I gotta get these planes into Maple's memory. So select, hold down the control key, and drag it over. It's equivalent to copy paste. It's not a Maple thing, it's a Windows thing. And you can do that in Mac and Linux in an equivalent way. Go here to the context panel, student multivariate calculus, lines and planes, plane. Default variables, X, Y, Z, okay, that's what I use. Maple has created what it calls a plane object. That's the symbol for this plane object. Think of it as a basket into which all the properties of this plane are tossed. I think technically it's a module, and I want to give that a name, so assign to a name. Q, and I use square brackets to get a subscript because I'm working here in 1D math. I have to do the same thing for the second plane. So do exactly the same thing. Drag it down. Make plane. Give it a name, and I'll call it Q2. Okay, now we want the distance between these two planes. So we write a sequence of the names, Q1, Q2, and I want to do this evaluate and display in line, which I can do from the context panel, or I can do it from the keyboard, which is what I normally do. And there are two different ways to do it from the keyboard. Control equal, which is what I do, or Alt Enter, I believe, is an equivalent. Okay, so now Maple sees what those two names actually are. Go to Student Multivariate Calculus, Lines and Planes, and says, oh, you have two planes here. These are the things you can do with a pair of planes. You can find the distance between them, 12 over the square root of 29. Then Maple rationalizes that square root. And if we want to see what that is as a floating point number, 2.22 or 2.23, I guess, if you round it quickly. Now, in a typical calculus book, this problem is solved by a projection. You get a point on each plane, draw a vector between those 2 points, you project that vector onto the common normal. The length of that projection is then the distance between the planes. So we can implement that here using the same suite of tools. Write the name of the plane, Q1, control equal, lines and planes, and you notice that you have the option of picking a point. So we have picked a point. Now, the square brackets indicate that this is a list. We're going to want this to be a column vector. So we go to conversions, and we convert that to a column vector, which represents a point. So this is the radius vector or position vector representation of that point. And we give it a name. I'll use P1 and P2 for the names of these points. P1. We have to do the same thing for the other plane to get a point on the other plane. So Q2, control equal, lines and planes, get a point, convert that, conversions, convert that to a column vector, give that a name. So to a name, this will be P2. Then we need the difference between P1 and P2. So P2 minus P1 is a vector from P1 to P2. So we write P2 minus P1. Control equal. So now Maple sees that vector, and we want to give that a name, and I'm going to give it the name little v, lowercase v. Okay, so that's the vector between these 2 points, and we want to project that onto the common normal. Now we can read off the common normal from these planes. That's easy enough to do. Go back to the equation of the plane. 2, 3, 4 is the common normal. So we want a sequence of this name v and the common normal 2, 3, 4, where these wedge brackets are just inequality symbols. Control equal. So now Maple can see what that sequence actually is. And go back here to Multivariate Calculus, lines and planes, projection. So this is the projection of v onto the common normal. And I want to know the length of that vector. So there is a norm command in here, 12 over the square root of 29. So that's typically what's done in a calculus book. And here we've implemented that approach using this suite of tools that have been added to the multivariate calculus package. Now, a solution from first principles really is a solution without use of these wonderful lines and planes tools. So the picture that I described verbally is here drawn. Here are the 2 planes. Pick a point on one plane, pick a point on the other plane. This is the vector that we call little v. It's from one point to the other. This red vector is the common normal. The projection of the green vector onto the red vector is actually this black vector. I put it out here so it would collide with the red vector. And it's the length of this black vector projection that constitutes the distance between the 2 planes. The calculations that you would do without these wonderful lines and planes tools would be something like this. You would need the common normal. So let's give that the name n. use plus sign equals. Use these wedge brackets to make a vector, 2, 3, 4. And here, if you say assign name, Maple will just make the assignment here. We need a point on each plane. One plane will be A, the other one will be B. Now, to do that, we don't have this tool that gave us a point on the plane. We have to find it. So what I'm going to do is I'm going to set x and y equal to 0 and find what the corresponding z is on that plane. That'll be my point, 0, 0, and that z value. So we need the equation of the plane. I think it's going to be faster to just do 2x plus 3y plus 4z equals 5. And then set x and y equal to 0. So I will use this evaluate at a point. So x will be 0, y will be 0. You can pick any numbers. And then you solve this for z. Clearly it's 5/4. Solve that for z. And then you want to substitute that into the vector 0, 0, z. So you get 0, 0, 5/4. So you use a substitute into. We're going to substitute into 0, 0, z. And that's the vector form of the point A. It's the position vector form of the point. And I will give that the name A. Now we have the same thing for a point on the other plane, and that is B. So I think what I'll do here is I'll steal this thing, drag it down, change the 5 to a 17. Substitute, again, I'll use 0, 0. Evaluate at point 0, 0. Solve this for z. So solve 17/4. I do substitute into bracket 0, 0, z. And I give this the name B because it's the position vector form of point B. So assign to a name B. And then by differencing, you get the vector from A to B, or B to A to B. So we'll do V equals B minus A. And if we do an assign name, maybe we'll do the computation and assign it to the name V. So the scalar projection that we need here is V dot n over the norm of n. So we can write V, and I have a dot product here, which I get from my common symbols palette. You see here's a dot, here's a del operator, here's a cross product operator. You click on one of these things, right click on one of these things, and you get the option to add to favorites, and that is how I populated this palette, my favorites palette, with stuff that I use on a regular basis. Okay, V dot n, then I want to divide by the norm of n. So I will divide, and then 2 strokes, n, 2 strokes, norm of n. Control equal, 12 over the square root of 29. After that unit on vectors, lines, and planes, the next thing that shows up in the course is a study of surfaces studied through things like level curves in plane sections. So what does Maple have to offer for looking at level curves in plane sections? But you got to remember now, You're using a tool like Maple, you can draw the surface. You don't need a tool like level curve and plane surface to visualize the surface. You can already visualize the surface. So it's a question of what do level curves and plane sections tell you about the surface after you've seen the surface. Maple has a tutor for this. So what are the tutors? They're pop-up tools. Tutors. Multivariate Calculus. Okay, you see this cross sections tutor? It's a pop-up tool. So that's what I'm going to use. But I'm going to access it through the context panel. I need to load the package. Tools. Load package. Student. Multivariate Calculus. I need this expression for z, so I'll drag it down. Control drag here. Control drag. Student Multivariate Calculus. Tutors. Now I can access the tutors that make sense to inflict on this expression, cross sections. And it brings up the tutor and it has the expression in it already, so I don't have to worry about getting the expression in there. Notice down here that there is a cross section command that's really doing all the work over here. But this is a point and click syntax-free approach to that command, the benefits of that command. Okay, so you have an image of the surface. The default here is 5 horizontal cutting planes distributed between z equals 0 and z equals 32. But if you look at the axis here, it goes from 4 all the way down to minus 150. So you really need some negative numbers in here. So you really need something like minus 140 to 0. And if you do 5 cutting planes, you see what I call level curves. The literature calls them something else. Level sets. They like the term level sets. But they're curves. I call them level curves, right? Okay, you can animate and you can have one such cutting plane traverse the surface. You can get plane sections. So you would do that. Let's take plane sections x equals. So x equals, I'll go minus 3 to 3. And maybe I'll do more than 5. Try 15, see what that looks like. Animate. So now I have plane sections. Those green curves are the plane sections, and they're traversing the curve. If I click close, then that animation is written to my worksheet, and I can make use of the animation tools. So I could tell this animation to keep going and go back and forth and just keep chugging along. So now you can watch the level curve, the plane sections being drawn back and forth. You can speed it up or you can slow it down. And you have this syntax-free way of getting all of these images that you would struggle to draw and struggle to put together into visualizing the surface. Well, you've got the surface and you can see what plane curves and level sections are all about. Next big topic is differentiation, so partial derivatives, chain rule, and then some of the uses, or tangent plane would be one of the uses. Another use would be optimization. So here is an unconstrained optimization problem. It's a graphing problem, max, min, and use that to find out something about the surface. So let's just take a look at what Maple has to say about max, min. So I want to find and classify the extreme points of this function. Well, certainly we should draw a graph and see what information we can get from a graph. So we need to reference this function several times. So let's write f equals, drag this stuff down, drag the rule of the function down, and we'll just assign that name. So assign name. So now we can reference f. So type f, hit the enter key. Here's the rule. I want to draw its graph. So I go over to plots. I'll use this tool called the plot builder. I'm drawing a 3D plot. So you can see that Maple has defaulted to a minus 10 to 10 domain, and you get these big numbers like 1600. So we should make some modifications. So instead of going minus 10 to 10, why don't we go minus 5 to 2 in x? Then in y, how about minus 3 to 3? And then for the vertical axis, we'll be down here, let's say 8 to 15. I mean, these are numbers I discovered by experiment. So we have a much nicer looking graph. You can see that it has definitely a minimum. You can try to estimate where that minimum is, but now you know that you're looking at a function that has a minimum. You can get a numeric estimate of that minimum by using this optimization option, looking for a local minimum. So the local minimum appears to be 9.6, located with the x and y coordinates given by these two amounts. So you get some rough idea of what it is that you need to find analytically by the techniques of the calculus. There's a task template that we're going to use. Now, what are task templates? Task templates are pop-up tools. Tools, tasks, browse, table of contents, calculus multivariate, optimization, critical points, and second derivative tests. So here is a test template. It can be embedded in your worksheet by clicking one of these insert buttons. Default content gives you this extra verbiage. Minimal content gives you enough to make the thing work. And I've got it embedded in my worksheet already. So here's the path to it we just saw. What do we want to do? We want to get information into this task template. So I select this field, type the name F, and hit the enter key. And so now we have entered that expression. Now the list of independent variables is x and y, so we can live with that. And you'll note that we are invoking some commands, the gradient command, for example. So what are the components of the gradient? Derivative with respect to x and a derivative with respect to y. And Maple is getting its information from these equation labels. Equation label stands for the thing that it labels. And so this command needs only to be executed. So here are the two partial derivatives. They need to be set equal to 0. And notice that we're hitting it with a solve. Maple assumes you meant equal 0, so you're going to find critical points. This extra coding takes the form that solve delivers and puts it into the form for the next command, which is the second derivative test command. So that has to be a list of lists. So each critical point that gets found is reported as a list, and if there are multiple critical points, you get a list of lists. You then apply the second derivative test command to that list. See, equation label here, equation label here. just hit the enter key, and for each critical point found, Maple categorizes as local min, local max, or saddle. Well, there was only the one critical point, and it has been categorized as a local min. You can also use the second derivative test as follows. You produce here the Hessian, which is the matrix of second partials. If that's positive definite or negative definite, you are then either adding to the minimum value in the neighborhood of the minimum or subtracting from it. Now, if you use your hands in the shape of a bowl opening upwards, you realize you're adding, so you have a minimum. If you turn your hands downwards, you have a maximum. Now, the definiteness of the matrix, because it's symmetric, can be determined by its eigenvalues, and its eigenvalues are printed right here. You can see that square root of 53 is less than the square root of 64. So this is a positive number. So both these numbers are positive. So you have a positive definite matrix. You are adding to the minimum value at neighboring points. So you have a minimum. And the value of this is the typical calculus text does not tell you how to classify critical points if you have three variables. So here is a way to classify critical points for more than just the two variables that are in the calculus book. You can look at the Hessian and see, because it says here output equals Hessian. Look at the Hessian and you find out its definiteness. And Maple has click type commands for determining if queries. Is it positive definite, negative definite, what have you. To solve this problem from first principles, you'd first have to get the critical points, and then you would apply the second derivative test. So how do you find the critical points? Well, you have to solve these two equations, the partial with respect to x and the partial with respect to y. You set them equal to 0. So you can go up here to the calculus palette and select this partial derivative operator, x, tab, put an f, set that equal to 0, comma, put another partial in there, and you differentiating with respect to y, tab f, set that equal to 0. These, oh, I didn't say equal to 0. I just put a 0. Equal to 0. It's nice that you can just fix that up right on the keyboard, and it all looks good afterwards. Okay, you have to solve these two equations. So go here to solve. Pick the simplest solve. You have the minus 17 over 11 minus 2 over 11. And you can see the difference in format. Up here, to make use or to anticipate the use of the second derivative test, which requires a list of lists, this format of a set of equations had to be transformed into a list of lists. Okay, so let's apply the second derivative test. So you need second partials because you're going to form this test number, fxx, fyy minus fxy squared. So we need second derivatives. So we can again go to the calculus palette. There is a second derivative operator here. Two derivatives with respect to x applied to f. That number is 6. I just did a control equal. We use the same template with differentiating twice with respect to y, tab f. That number is 10. The mixed partial, there's an operator here, this one. I want y to be taken second. I want fxy. I want y to be taken second, so it goes on the outside. Y tab x, tab f. That number is negative 7. So what do I have to put together? I have to put this number together. So it's 6 times 10, which is 60. Let's just do that, 60, less this number squared, less 49, which is a positive number. So you're down here in the calculus book criteria. This number is positive. This number is positive. So you are positively positive. So if you put your hands in the shape of a bowl, you will see that you have a minimum. Well, we just did an unconstrained optimization problem. Let's do a constrained optimization problem, which is essentially a Lagrange multiplier problem. So the problem is extreme values of this objective function, xy, subject to the constraint g of xy equals 0. So let's initialize things here, get started. I want to work in the multivariate calculus package. So tools, load package, student multivariate calculus. Then I pre-typed some stuff here. I want to define f. So I typed it, and I will do an assigned name. And the function g, right? Not the equal 0, which it makes it an equation, just the function g, everything brought over to the left side, we'll do an assigned name. So we've got the data in there now. There's a pop-up tool called the Optimization Assistant. Now, assistants are up here, and they've moved the Optimization Assistant from this category to the tutor category. So it's actually down here, but I'm going to access it through the context panel. So we want a sequence of the function and the constraint equation, which is g equals 0. And on that sequence, I will launch this tutor, this assistant, which will give us a numeric solution. So the function and the constraint, and let's see if we can find a minimum. We click solve, and it says, well, you must be sitting so close to the minimum that can't do any computations. So let's change the default starting point. I'm going to just jump it out to 3, see what happens. Click solve. Okay, so it found something. And what I want to show here is that you can get a numeric optimization, but there is this plot button which draws a really nice picture. But this picture has its domain too close to the extreme that we just found. So let's back out. Let's go -3 to 3, -3 to 3. And let's see what the picture looks like now. Now you see the saddle surface. And now you see the constraint circle drawn on the saddle surface. And you see an extreme point. And if you click that you want the constraint drawn as a surface, you see it as a cylinder piercing the objective function surface. And that shows you how that lift is made to the surface. And I think this graph is a useful addition to the study of constrained optimization. So now let's get into this Lagrange multiplier method directly. So there are several ways to access it. One is through the context panel. So you write a sequence of the objective function and the constraint function. And over in student multivariate calculus option, you pick Lagrange multipliers. You give it a list of the variables, which would be x and y. and you have a choice of what you can get back out. You can just have it give you the value. You could have it give you some detailed information. It draws a graph, but we've seen a graph. Okay, so let's just say value, see what happens. Okay, you get 4 critical points. If you do this again, F comma G, you do this again, you go here to student multivariate calculus, Lagrange multipliers. It's remembered X and Y as the variables, you say detailed. What you get now are these equations that give you the X and Y coordinates, the Lagrange multiplier, and the function value for that critical point. Okay, so this is a more detailed output from the Lagrange multiplier command, which is in student multivariate calculus and which is implemented syntax-free through the context menu. The Lagrange multiplier method can be accessed through a task template. Now I showed you where task templates can be found, and here's the path to it: multivariate calculus optimization, Lagrange multiplier method. Here is the task template. It's already been embedded, so we can put F here, we can put G here, and we put a list of variables X comma Y here, and this button is actually executing this Lagrange multiplier command. The output is in a little bit neater format. You read down these columns: X, Y coordinate, Lagrange multiplier, function value. So here are the 4 critical points in a more readable format. Then finally, access Lagrange multiplier method through first principles. Several ways to do it. Here's the way I've chosen to do it. Let's write F minus lambda space for multiply G. And let's give that the name F. So assign to a name uppercase F. We differentiate that function with respect to X, Y, and lambda. So the partials with respect to X and Y are set equal to 0, and the partial with respect to lambda reconstructs G set it equal to 0. That throws in the constraint equation. So we can obtain these partials by going back to this calculus palette. Partial derivative operator, differentiating with respect to X, tab over here to F. And whether you put equals 0 or not, it doesn't matter. Maple will assume that you meant it if you don't do it. Another derivative here with respect to Y, tab F equals 0. And the derivative with respect to lambda on F equals 0. So those are the 3 equations you need to solve. They are nonlinear. There is no recipe for solving a set of nonlinear equations. The only thing that you can say to a student is don't cancel. You can factor, and you can apply the 0 principle. Products equal to 0, one or the other factor has to equal 0, even both. Okay? So this is difficult. At this point, I found it very helpful to use Maple's solve command. Here, the simplest solve will work. When the student gets the idea of what you're doing and why this works, you can spend time, if you like, on the algebra of solving sets of nonlinear equations. But if you make the solution of sets of nonlinear equations preeminent, then the message about Lagrange multiplier recedes to the background, and I think runs the risk of getting lost. An integration problem next. Multiple integral. Volume between 2 surfaces. So here is an upper surface F and a lower surface G. And that portion of the surfaces that lies inside this right cylinder, and I described the cylinder by its footprint, its cross section, and the planes equal 0. It's bounded by the curves y equals x, y equals 2 minus x squared, and x equals 0. So just before we jump into this, let's just visualize this footprint. Y equals x goes like this, 2 minus x squared goes like that, x equals 0 goes like that. So part of this problem is going to be draw that region. Let's draw that footprint. Well, let's start with 2 minus x squared. And we can make use of this plot builder. And we're drawing a 2D graph. Default is minus 10 to 10. We really need to only start at 0 and no more than 2. So let's start at 0 and go as far as 2. And we could have gone to 1.5. But at any rate, we want to add to this the graph of y equals x. So suppose we grab this x and copy it. Let's see, we want that to be executable. So let's make that executable. Then we can copy that. And we're going to paste it on here. And this is the region that is the cross section in the planes equals 0. X equals 0, 2 minus x squared. So it's this stuff here. We need to get some data into Maple's memory. The functions f and g. So let's do a control drag here. Drag the first one down and do an assigned name. And then drag the second one down and do an assigned name. So now Maple knows f and g. There are two ways to set this volume integral up. It could be set up as an iterated double integral or as an iterated triple integral. And we'll take a look at both. So visualization. Can we see regions, etc.? So here is a task template. Here's the path to it. I've got it embedded. Are we going to integrate dy dx or dx dy? Well, if you remember what the region looked like, you pick dy dx as the order of integration. These would be the bounds, and this would be the integrand. Now, the integrand is going to be f minus g, because f is on top, g is on the bottom. And you can tell that f is on top. That 7 is higher than this -3, so it's f minus g. F minus g here. You're integrating from x upwards. So this bound here is x, and this bound here is 2 minus x squared. And you're going 0 to 1. Now, how do I know we're going 0 to 1? Well, if you go back to this cross-section image, you can convince yourself either graphically or by solving the appropriate equation. 2 minus x squared equals x, x equals 1. So we're going 0 to 1 here. 0 to 1. Well, this would be the value of the integral. And this is the pair of graphs that I think you might want to look at. This arrow is telling you to integrate in the y direction first. So this is what's telling you to integrate from x to 2 minus x squared. This is the region bounded by f minus g, z equals 0, x equals 0, x equals 1, x and 2 minus x squared. So this is y equals x, that plane. This is the curve 2 minus x squared drawn up as a plane. And this is the top of this region. And you see the volume is in quotes because this is not the volume you're finding. This is not an image of the volume you're finding. This is an image of the region over which this double integral takes place, which ends up giving you a volume. But this picture is not the picture of a volume. So with this help here in front of us, let's dig down and see if we can do something about setting up this integral ourselves. We'll work in the Student Multivariate Calculus package. So Tools, Load Package, Student Multivariate Calculus. So the integrand for the double integral is going to be f minus g. We go over here to Student Multivariate Calculus. We have integrate iterated. And we have a pop-up that lets us give the variables of the balance. So we're going to integrate y first. We're going to do a dy integral, and then we're going to do x second. The ranges. Well, we know that x goes from 0 to 1, 0 dot dot 1, and we know that y goes from x dot dot 2 minus x squared. And we can get back the value of this integral. We can get back the unevaluated integral, and we can get back the integral stepwise, evaluated stepwise. So let's try the stepwise and see what happens. So here is the value of the integral. Here is the integral. This is the integrand. This is the inner integral, outer integral. It's dy dx. And here you see Mabel doing it stepwise. First, it integrates with respect to y. So, for example, this minus x squared picks up a y. The y squared goes to y cubed over 3. The x picks up a y. The y goes to y squared over 2. The 10 becomes 10y. And you evaluate this between y equals x and 2 minus x squared. When you do that, you have all of this now. Well, clearly, if you were working with a pencil and paper, you would simplify all of this first. And then you integrate that with respect to x. So this is now the integral, the antiderivative with respect to x, and you evaluate that between 0 and 1. So that's the stepwise result. The value you're going to just get 1143 over 140. And if you choose, that's the same. If you choose here instead of steps, the integral, you get the unevaluated integral, okay, which you can evaluate by going here to, I guess it's this one here, evaluate integral, okay? Let's do the same thing for a triple integral. First, let's see what kind of pictures we can draw, and then let's look at the integral from first principles. Okay, so you have now 6 choices for the order of integration, but from what you've detected so far, you might realize that you want to go dz, dy, dx. In this case, the integrand is 1. because the f and the g end up here. So the lower boundary is g. The upper boundary is under little f. This bound is x. This bound is 2 minus x squared. And then 0 to 1 in x. 0 to 1 in x. Now, we can get an exact value, and we can get a graph. This time, the region that you see is precisely the volume that you're computing. This is y equals x. This is 2 minus x squared lifted straight up. This top is now f, and this slanty bottom is now g. Okay, so this is a more accurate rendition of the volume that you are computing. If this were not a 1, if this were a volume integral of some temperature distribution or whatever, then you would get the same region, but it would not represent a geometric volume, but it would be the region over which you are integrating. So let's take a look at this integration again from first principles. Now we've already installed a package. We don't have to do that. So the integrand is 1. Student multivariate calculus, integrate, iterated, dialog comes up. This is now Cartesian 3D. And we're going to go z, y, x, and the ranges, we know x is 0 to 1. Y is x to 2 minus x squared. And in z, it's from bottom guy, which is g, to the top guy, which is f. And again, we have the option of just give me a value, write out the double integral, or give me the steps. So I'll pick steps, and you see here, this is the integral being evaluated. This is the triple integral being evaluated. Integrand is 1, dz, dy, dx, and stepwise, you integrate with respect to z first, so you get a z. And then you evaluate between these two limits, and you get this function of x and y. And if you are very observant, you realize that this is what you had when you did it with a double integral. And this double integral is essentially the same as what we saw for the double integral.